Hi all. Today we discuss the relation or connection between uniform convergence and continuity. So before we going to discuss the theorem, we will see a situation like this. If you have limit n tends to infinity, or first of all we will consider a sequence, a double sequence, say m by m over m plus n. As m is equal to n is equal to 1 2 3 etc, and m is also from 1 2 3 etc infinity. Now if you consider such a sequence and it is denoted by smn, I denote this sequence as sequence smn. Now if you consider this sequence, then you can consider the two different limits. One of the limits is as limit n tends to infinity smn, and you can consider limit m tends to infinity smn. Okay, so therefore we can consider limit m tends to infinity, limit n tends to infinity smn. Okay, so for a double sequence, or if we can consider two different limits, then you can consider the limit one by one. So this will give limit m tends to infinity, limit n tends to infinity. This will be limit n tends to infinity first, then limit n tends to infinity smn. Smn is m upon m plus n. Okay, so this is the case. Then if you take the first limit, the inner limit, you will get limit m tends to infinity. What is the first this limit? By fixing m, n tends to we will let n tends to infinity. So denominator gets increased, and this tends to 0. So we have limit m tends to infinity 0. So this will give 0. Okay, but if you consider the limits in the other way around, limit n tends to infinity, limit m tends to infinity first. In this case, we need to take a limit m tends to infinity first. So we take this limit first, limit m tends to infinity, m by m plus 1, m plus n. So by fixing n and make this limit, that will give as m tends to infinity, this tends to infinity, this tends to infinity, or you can rearrange by dividing throughout by m. Then this will be 1, this will be 1, and this will be n by m. By dividing throughout by m, you can get this as m tends to infinity, this tends to 1. So the limit will be n tends to infinity 1. So that will be 1. That means if you interchange these two limits, now if we interchange these two limits, we can get two different answers. Okay, the one is 0 and the other will be 1. Okay, the for a double sequence, or if you can discuss two different types of limits, then that limit, if the interchanging of limit will never get the same answer. Okay, so in case of our functions, limit fn, the sequence fn, as we discussed in the definition of the uniform convergence, if we consider the sequence fn, okay, then if we for this fn, we can consider two types of limit. As limit n tends to infinity, you can consider this limit fn of t, or the other way you can consider limit t tends to x. Okay, fn of t. These two types of limit can be considered for this sequence of functions fn. Okay, so this will lead to the continuity of this. If this is some fn of x, then that will give the continuity. So we never expect this, but anyway, you can consider two different kinds of limit in this sequence. Okay, but the previous exercise shows that the interchanging of this limit n tends to infinity fn of t, limit n tends to infinity fn of t, limit n tends to infinity, limit t tends to x fn of t need not equal to limit t tends to x, limit n tends to infinity fn of t. Okay, so in general this is not always true, that is this never equal to this one. Okay, but uniform convergence, this is the connection of uniform convergence to the continuity. So if you assume the convergence, if this Fn converges to F uniformly, then we can expect this result. This will be the same. Okay, this is what we have discussed in the next theorem. So next theorem is theorem 7.11, that is the convergence, the limit can be interchanged. This can also be considered as the theorem which shows the limit can be interchanged in case of uniform convergence. This is the theorem. Suppose Fn converges uniformly on set E in a metric space. Let X be a limit point of E. So that means there is a sequence which converges to this X. And suppose that limit t tends to X, Fn of t equal to An. So we denote this limit exist and it is An. Then sequence An converges and limit t tends to X, F of t equal to limit n tends to infinity An. Okay, so this is the theorem in which we use the idea that limit can be interchanged. That is because if we substitute the values for this on the other way, otherwise you can write this equation as limit t tends to X. We replace this F of t by limit n tends to infinity Fn of t. Okay, this is the limit F of t. Then that means our assumption is Fn converges to F uniformly. That means limit n tends to infinity Fn is F. So we replace this F of t by this quantity. Then this is limit n tends to infinity. We replace this An by this result, limit t tends to X, Fn of t. So this will give the idea that limit can be interchanged. Okay, so we will prove this theorem. For the proof, our assumption is this Fn converges to F uniformly. So we assume Fn converges to F uniformly. That is, for epsilon greater than 0, there exists n such that, this is the definition, modulus Fn of X minus Fm of X less than or equal to epsilon for all n greater than or equal to n, for all m greater than or equal to n. So this is the Cauchy criteria for uniform convergence for all x belongs to E. Okay, now by fixing, first of all we need to prove that this the sequence An converges. So in order to get the sequence An, we need to take the limit on this. Okay, by taking take limit t tends to X on both sides. Okay, both sides of this equation, then that will lead to An minus Am less than or equal to epsilon for all n. So first we write this is in t, then only you can take the limit. We write it as in t. This is true for Fn of t minus Fm of t for all t belongs to E. So that is the definition. I rewrite the definition in terms of t. Then you can take limit t tends to X on both sides. Then that will be Am from this definition, and the second term will be Am less than or equal to epsilon for all n greater than or equal to n, for all n greater than or equal to n. So this is the Cauchy criteria for convergence of sequence of the sequence An. So this implies sequence An converges. Okay, so if this is convergent, then we can expect a limit, say A. Okay, An converges to A. Now we can replace this quantity as limit n tends to infinity An by A. So it is enough to show that, in order to prove this theorem, it is enough to show that limit t tends to X f of t is equal to A. Okay, that is enough. This A is taken as the limit of An. Okay, now we will show that Fn of or f of t. Okay, so we need to prove that limit t tends to X f of t equal to A. For that we prove f of t minus A less than epsilon for some in some neighborhood of this x. Okay, so for all t minus x less than epsilon, okay, less than delta, this is less than delta. Okay, though whenever, this is what you have to prove. Okay, now we write, to prove this, we start with f of t minus a. Now we insert some terms in between this f of t and that a, that is, first we insert fn of t, f of t minus fn of t plus fn of t. So we have inserted fn of t, then we have an minus a. Okay, so these are the terms. We have inserted this much terms in between that f of t and this a. Now we split, using the triangle inequality, we split this as f of t minus fn of t plus fn of t minus a. We collected these two, plus an minus a. Okay, this is the triangle inequality. Now we can make this is less than or equal to epsilon by 3 as this fn converges to f uniformly. Okay, so this can be made less than epsilon by 3 for all n greater than or equal to n and for all t belongs to e. Okay, now you consider this fn of t and an. Okay, we have already shown that as limit t tends to x, the relation between these two, limit t tends to x, fn of t is equal to an. That is the notation here. So this shows that for every epsilon greater than 0, then we can get epsilon by 3 is also greater than 0. Then there exists a delta greater than 0 such that mod fn of t minus an less than epsilon by 3 whenever mod t minus x less than delta. Okay, so this can be made less than epsilon by 3 for all t satisfies mod t minus x less than delta. Okay, and plus this we are already seen that this an converges to a, so this can be made less than epsilon by 3 as n greater than or equal to some n prime. Okay, so this will be, this f of t minus a is less than epsilon for all if we choose a particular n which is greater than both this n prime and n. Okay, if we choose an x such that which is greater than both this n prime and n, then you can make this f of t minus a less than epsilon whenever this mod t minus x less than delta. Okay, which shows that limit t tends to x, f of t is equal to a. Okay, so that implies limit t tends to x. What is f of t here? F of t, we write this f of t itself, and what is a here? Limit n tends to infinity an. Okay, which shows which proves the interchanging of limit. Okay, so this is the proof of theorem 7.11. In the textbook, they are not using this modulus. They are using, we are dealing this theorem with in a metric space. So we can consider instead of taking this modulus, we can replace this by some distance function d, or not even a modulus. You can replace this by a general distance function d, or you can use a open set v intersect with this. The open set about x. Okay, we intersect the open set about x intersect with this e, so we can replace this by this result. Okay, now as a consequence of this, we will prove the theorem, next theorem, theorem 12, which shows that the uniform limit of continuous function is continuous. Okay, so that is the next theorem. So that is theorem 12. That means if you consider a sequence of functions, fn is a sequence of functions continuous at x. Okay, now the limit function is also continuous at x. That is the theorem. So we write the statement of theorem 12. This is the statement of theorem. If fn is a sequence of continuous functions on E, and if fn converges to f uniformly on E, then this limit function f is also continuous on E. So we prove the continuity of this f using the uniform convergence. So we fix an x, let x be an element of E. So we fix an element from E. Now we will prove that limit t tends to x, f of t is f of x. So we start with this limit t tends to x. By definition, this t f of t can be written as limit n tends to infinity fn of t. But we have proved that if the convergence is uniform, you can interchange these two limits. So we interchange these two limits, limit n tends to infinity first, then limit t tends to x, fn of t. But we are given that fn of t is continuous. Each fn is continuous. So this will be limit n tends to infinity. Fn of t is, since fn of t is continuous, then this will be fn of x. Okay, now use the uniform convergence, limit n tends to infinity fn of x, that will be f of x. Okay, now we have limit t tends to x, f of t is equal to f of x, which shows that f is continuous. That is the uniform limit of continuous functions. A sequence of continuous functions is again continuous. Okay, so this proves theorem 12.